going to talk to us about exceptional low latency C++. Phil Nash.
Hello. Good morning, everyone. So, as Timo said, I'm developer advocate at JetBrains. So, if you haven't come by the booth yet, please come and say hello. We're very friendly, and we can talk about anything to do with C++ and beyond. In fact, even if you have come back, see us again, because we're a bit quieter today. But that's not what we're going to talk about today. I'm going to talk about exceptional low latency C++. And to some of you, this slide might look a little bit familiar. That's deliberate. Get onto that in a moment. In fact, we'll get onto that now. So, who's familiar with this book? Right, so yeah, about a quarter of the room, I'd say. So yeah, I realised when I was putting this together that it's actually sufficiently old now that there's plenty of people in the industry that probably never even seen it. This was a really important book about 15 years or so ago. And the title of it, Exceptional C++, alludes to the fact that although exceptions had been around in the language for at least 10 years at that point, there were things in the language and the ecosystem that meant that our understanding of how exceptions work was just coming together at that point. You know, with strong exception guarantees and transactional semantics and things. And we were really proud of our use of exceptions in C++. So this book is sort of the spiritual successor to Scott Mayer's Effective C++ series from before that. And Herb followed it up with more exceptional C++. So yeah, he really liked this exceptions thing. And he even went on to do exceptional C++ style. So he was all in on exceptions. It was the primary, or still is, the primary mechanism for error handling in C++. Really important. But how many people in this room work on a project where exceptions are completely disabled? Quite a few. And how many people avoid exceptions, at least in certain critical parts of their code, for performance reasons? Right. Quite a few. Not as many as I thought, actually. I thought it'd been like nearly everyone here, but that's interesting. So in the 2018 C++ Foundation Developer Survey, the bit in yellow quotes 52% of C++ developers. So not necessarily restricted to low latency or other parts of the industry that are more sensitive to this, but of all C++ developers, 52%, more than half, reported that their exceptions were banned in part or all of their project code. Goes on to say, i.e. most are not allowed to freely use C++'s primary recommended error handling model that's required to use the C++ standard library, standard language and library. And you see, this is a quote from Herb Satter again. Who wrote the book on this? So he realizes this is the problem, that more than half of the industry is not using that primary recommended error handling approach. And why is that? Well, there's a few reasons. This is one of them. Performance. So just the raw performance. There are no really completely representative figures on the cost of exception handling for a number of reasons, but a few people have put together their own benchmarks that we can get some insight from. This is one I stole from Niall Douglas, who did a talk last year at Meeting C++. The yellow bars, appreciate you probably can't read this very, very clearly. The yellow bars are the cost of throwing an exception up 10 layers of stack on an x64 platform. Whereas the other bars are different types of returning error codes. A few variants, doesn't matter what they are. The y-axis is exponential. That means that this cost is effectively 2 to 3 orders of magnitude slower in the case of exceptions. This is on the error path, so when an exception is actually thrown. I should be clear about that. Actually, the cost is very good when there's no exception thrown, which is what we've been optimizing for all these years. So raw performance, if you care about the error path, is absolutely abysmal. And I think for this audience in particular, maybe the even bigger problem is the determinism involved. The fact that sometimes it will perform quite well and other times it just goes off the charts, and even this doesn't capture that completely, particularly if it has to load like an additional part of the executable image into memory in order to process the exception handling table. I'm not going to get too much into the details of that. There are other talks that do that, but just wanted to make sure that we're all clear that this is really the reason that there's a problem. In fact, there's a couple other problems as well. We'll come on to that a little bit later in the talk. This talk is not actually about exceptions as such. We're going to pass through that. It's about error handling in general. There's lots of different approaches, and we're going to talk about them. So one reason for that is there's different types of error. Lots of different types of error. What we're going to do is look at some of the characteristics of certain buckets of error so that we can reason a bit more clearly about what type of error handling approach we need, and ultimately whether we can try and unify those approaches. So an old favourite of mine, the classic "this should never happen" error. Now, I'm sure we've all seen this. We've probably written this message ourselves, and I'm sure our users have seen this from time to time, which is a bit of a problem. In fact, this beautiful moment of irony, when I was preparing these slides originally, Keynote crashed on me at exactly this point and gave me the stack dump. So the point is, we have code where we say, this should never happen, this particular situation, and yet it does. We need somehow to be able to allow for that. And there's various techniques. So that's one category of error. This should never happen. There's two others I want to look at. So there's should not usually happen, which is somewhat awkwardly worded. I'll show you why in a moment. And the might happen, what we prefer if we didn't, even more awkwardly worded. But this is actually probably the most common category, and also where we're going to spend most of our time looking. But just put some examples to that. So the should never happen, of course, of things like null dereference, out of range, and so on. Those things that, if they do happen, they represent a bug in your code. There's no other way to look at it, really. Literally, this should never happen. If they do, it's because you've done something wrong, or part of your system has done something wrong. They should not usually happen, though. These are things that we often rely on not happening, like being out of heap memory. In fact, that's the canonical example. But they can happen, and it's legitimate when they do. It's not a bug. It's just a fact of life that we have to deal with, which makes it really awkward to deal with because, particularly looking at out of memory, this could happen any time from almost any line of your code to a first approximation. And yet, it's really difficult to deal with, and a lot of the complexity of particularly exception handling in C++ is because of this case. There is a case for treating this specially. We'll look at that in a second. So the last category, very boring examples. You can read that. File not found, couldn't convert from a string, couldn't find key in a map. Just the run-of-the-mill, I'd like to do this, I couldn't, okay, I'll do this instead. We have to deal with that all the time. It's a bit closer to just normal control flow rather than a catastrophic error. We deal with this a lot. So there's a couple of ways we can bucket these. So first of all, just want to note, as we said already, the top bucket, these represent logic errors. They are bugs in your code, and we should deal with them as such. Whereas the bottom bucket, they're called I/O or side effects. If you think about it, if something goes wrong, it must be either to do with something in your code or from outside your code. It's really the only two options. So it makes sense to categorize them this way, except there's a couple little wrinkles to this. The first is that those bottom examples, well, sometimes they do actually represent bugs. Sometimes that file really must be there, or that string really must encode an integer. Whatever it is. The point is, whether it's a logic error or an I/O error, really depends on the usage rather than the implementation. If you're writing a function that converts a string to an int, well, how do you know whether your inputs have been validated or not? And yet we often encode our error handling strategy at the implementation side rather than the call site. And often that's almost the only way we can do it, because we don't really have the tools to express that well enough, and that's something we're going to come to at the end a bit more. So that's one little wrinkle. The other one is that middle one, which is really annoying, because up until now, we haven't really had a decent way to handle this. And the proposal is, and we'll talk about proposals a bit later, but the thinking that we're going to come onto is that for most platforms, it makes sense to not handle out of memory, but rather, if an out of memory situation occurs, to actually terminate at that point. In other words, treat it more like the top category. We didn't really say that, but actually the recommended approach to treating the top category is to terminate at that point by default. That makes things a lot simpler, but obviously there are some categories of system where that's not the right approach. So we're only saying doing this by default, but you can still have control both in terms of calling a version of new that returns null, for example, or setting the new handler so that it doesn't have this behavior. So you can still back out of this. But for most people, it makes sense for the default to be, don't worry about out of memory. And then we only have to worry about the top and the bottom categories. So we'll sort of treat that a bit off to the side. Then it makes sense also to look at it in terms of how we deal with these errors. So those I/O side effects errors, we can also call them recoverable errors, in that we expect to continue on after these things, we just maybe take a different path. Whereas the top errors, not recoverable, we really should terminate. And there are some people that say, well, actually, I've got this highly available, really resilient system, it can't afford to go down. Most of the time, that might be true, but handling it in code is probably not the way to do it. You probably want something more like process level isolation. Not really such a topic for this audience, but, and this is something I was talking to Timur yesterday about this. For people that write plugins, they may have their own ideas about this. What happens if terminate's called in a plugin? And I'm not sure if I have the complete answer to this yet, so maybe there are some people here can tell me, but I believe that's something that can be handled so that a plugin might go down without the whole process going down. This is actually a really interesting area for discussion, because this is something that's being actively discussed right now, and we need input from people who are actually implementing these systems to tell us where to go. So if you've got any ideas about that, please come and talk to me afterwards. We're not going to talk too much more about that today, though, other than to say that that top category is really what we call dealing with contracts. At the moment in C++, we have the assert keyword, which we can approximate to doing contracts. But there is a proposal coming, I'll give you the paper in a moment, that means that contracts as a more fully formed concept are going to be in C++ 20, have much richer handling there. The middle category, as we've said, proposal is actually we're going to terminate if we're out of memory, which leaves the bottom category, well, we're still left with exceptions or error returns. That's what we're going to spend most of the remainder of this talk talking about. So I mentioned contracts. There's the proposal that's in C++ 20. In San Diego a couple of weeks ago, there was more discussion on it, still actively being discussed, but it's definitely in 20. So this is going to change the way we write a lot of code. So it's worth becoming familiar with this if you're not already. So as well as the asserts that we currently have, we'll have the ability to specify preconditions and postconditions. There'll be the interface, more fine-grained control. You can control what happens when a contract is violated, but also say whether it's checked or not. There's a lot there, but it's not rocket science either. And this is going to be a big part of the standard library going forwards as well. So encourage you to look at that. As I say, though, we're going to spend most of our time looking at recoverable errors. This is where it gets interesting, I think. And I mentioned that there's a number of different approaches to error handling today. Exceptions is one of them. As we said, a lot of people here can't use exceptions in at least part of their code. So what do we do instead? We generally go back to things like returning error codes. And there are some newer approaches as well we're going to dig into. The thing is, how do we weigh these up? How do we know what the best thing to do is at any particular time? Which is best? And often when we look at this, we're looking at one or two key concerns that we're interested in. Like with exceptions, it's the performance or the determinism. But there's other factors as well. So what I'm going to try and do is actually weigh them up according to 8 different metrics and give them a score. So the first one is the overhead. So that's the performance, but also the determinism. I think that's really important. And I'm going to score it from 1 to 10, where 1 is bad and 10 is good. So it's sort of reverse from how I've stated it. And we also want to separate out the overhead between the happy path and the error path, because they can often be different and have different implications, which is why we are where we are with exceptions. But also want to look at the safety. So this is how hard it is to use or misuse a particular feature to get the right result. If it's hard to use, then you're more likely to make mistakes and you're more likely to end up in the bugs camp. Noise. Nobody likes noisy code with lots of boilerplate. Makes it hard to read, hard to reason about. Very often error handling is just lots of extra boilerplate on top of the code we actually wanted to write. Closely related to that, but I thought it was worth separating out, is this idea of having separate paths for the error path and the happy path. When they're all mixed up together, it makes it more noisy, but also makes it harder to reason about. So I think it's worth considering that one separately. Reasonability. Again, it's literally the ability to reason about what errors may occur, where, and how to handle them. And then composability is really two things. It's how much the error handling interferes with the ability to compose your functions and objects as they would have been without error handling, but also how composable the error handling itself is. So just put one score for this, but we'll talk about that more as we go through. And the final one is message. So how much extra information about what error occurred we can convey along with the error indicator itself. So hopefully this will become a bit clearer as we go through. So I want to start by looking at error codes. It's the sort of oldest, most traditional form of error handling, and what a lot of us have gone back to if we can't use exceptions. But there are definitely trade-offs, so let's have a look at that. An example I'm going to use is just a really simple function for creating a directory. So it takes a string, and in this example, returns a Boolean, the simplest possible way to indicate an error. And although the Boolean could represent anything, we know sort of by convention that if a function that's not a predicate returns a bool, probably indicates the success of the function. So it's a strong indicator. The usage case code is unsurprising, just an if-else, happy path and error path there. One thing to note is that because this returns something that indicates the error, let's say by convention we infer that, we call this marked propagation of the errors, because we can see in the signature that this is where the error is coming from and that we should do something with it. So it's something I'm going to come back to a bit, so I thought it was worth pointing that one out. So here's our scorecard for this one. So you can see the overhead is actually pretty good, as in low overhead, so high scores. All we're really paying for is the cost of returning the bool and the if-else check. And modern optimizing compilers and CPUs can do a pretty good job of optimizing that away almost completely, in fact. So maybe 9.5 would be a better score there. Safety, though, is pretty poor because it's very easy to just completely miss the return value and assume that whatever operation was has succeeded, which in some cases could be pretty catastrophic. So it can be very easy to misuse, so unsafe. It's pretty noisy as well. It doesn't show up quite so much here, but obviously the happy path is now on the inside of that if statement. So if you want to start chaining things along, you're going to get deeper and deeper nesting. It's very, very mixed up. There are ways to invert that a bit, but you're limited, so quite noisy. No separation of the happy path and error path once you get into nesting. And the composability suffers because we're using the return channel of the function to indicate the error, so we can't use that for composing functions. And the errors themselves don't compose very well. And beyond the fact that something happened, we convey no extra information, so pretty low message score. So that's how these scores are working. I'll try and move a bit faster through the rest. One thing we can do to make this better is to use the new no discard keyword. It came in C++ 17, I believe. And this will indicate to the compiler that if you don't actually look at the return code, it should issue a warning. Not guaranteed to, but it should do. So this will make it much harder to misuse, and so the safety score goes up. So that's good. We should definitely do that. Doesn't affect any of the other scores though. So let's see what else we can do. We can improve the message score by using a richer return type. So I've used an int here. Maybe an enum would be better, like an enum with different return codes. So at least you know what the error was. It doesn't give you any extra contextual information, like what parameters caused the error and that sort of thing. So I've only given it the halfway score. And it does make it a bit more noisy to use as well. So start to see how the trade-offs are coming in. One nice effect of this, though, is that in some cases, having that finer-grained view of what the error was means actually some of these things are not errors at all. If you're trying to create a directory and it already exists, you probably don't want to treat that as an error. So that gives you that ability. So that's returning error codes, but there's other ways that we get errors out of functions. One of them is by passing in a reference value, so an out parameter, if you like. So otherwise the same, but rather than the return channel, it's now a reference parameter. I think that makes it a bit harder to use. Now, it's a bit harder to reason about how you use that, so I've put the safety down a bit. And for the same reason, a bit harder to reason about. But potentially more composable, because now the return channel is free. We can use that. It's obviously not used here, but we can use that for composing functions together. So that's quite nice. I should point out, by the way, when these are my completely unscientific sort of finger in the air figures, if you disagree with the specific numbers, that's okay. Hopefully you'll sort of agree with the general analysis and the sorts of trade-offs we're talking about. So this is still marked propagation, because we still see in the signature that there's an error code coming out. We can mix some of these approaches to improve some of the scores. So this is quite a common approach. As well as the out parameter to say what the error is, we have the Boolean return to say that an error occurred at all. So safer to use, easier to reason about, but the composability suffers again. For the same reason, we're using that return channel. So maybe we try a completely different approach. Put the error code in a global variable, or maybe thread local storage these days. So that cleans some things up, but now we've got unmarked propagation. We can't see by looking at this function that it causes errors at all. It also impacts the overhead, because if we are using thread local storage to hold that error code, we're going to pay the cost of a thread local lookup every time we make that call, just to see whether an error occurred or not. Safety is way down because it's so easy to misuse this. And reasonability suffers as well for the same reason. It's unmarked propagation. But completely composable. There's nothing blocking the return channel, and it's less noisy. There's less things to go wrong. So different trade-offs. Now we might say, well, I'd never use this, but this is really common. Again, mixing approaches. Boolean return to say whether an error occurred. If it did, then we go and check this global or thread local variable. So that proves some things. It's a bit safer because we've got the Boolean. We can put no discard on there. Still easy to reason about, but composability suffers again. We're still blocking that return channel. So these are all the classic error code approaches that we're probably familiar with. You can see they all have their own trade-offs, but in all cases, apart from the thread local one, performance is actually pretty good, which is why these are still popular. So let's see where we go next. Let's briefly look at exceptions to see how they compare. Won't spend too long on this, but I think we'll just go straight to the scorecard, other than to note that, like the global variable example, it's unmarked propagation. So we can't reason about the error handling facilities of this function just by looking at it very easily. So overhead on the happy path is actually really good. Maybe even a 10. There is a fixed, constant overhead from using exceptions at all. Once you've paid that, you don't really pay any per call cost for exceptions, unless an exception occurs. And then it's really bad. We saw the figures at the beginning. I'm not going to go into that again. But safer to use, because if an exception occurs, it doesn't catch it at compile time, but at runtime you're going to find out pretty quickly. That's all done for you. Noise is pretty good, pretty low noise, so high score there, because really the extra keywords in there are just for the purpose of handling the errors, but it keeps the error handling separate from the happy path, so we've got that separate paths in there. It's reasonably good, easy to reason about, but because of that unmarked propagation, I can only give it a 5. Composability, though, is great. Not blocking the error path, plus the error handling itself is composable, because exceptions can propagate up the stack. You can put try-catches anywhere you want. It's all handled really nicely. So it's almost like the inverse of the trade-offs that we were seeing before with the error codes. But that's interesting to note, I think. And that's why generally exceptions have been very popular, where you're not worried about the error path. But we have noted the other big problem with exceptions is the ability to reason about them, because of the unmarked nature. So there's actually two problems with exceptions. Very briefly, should mention, well, we've still got that problem with what happens if the directory already exists. Probably a non-problem. There's other ways to deal with that, but something you have to think about. So I think it's fair to say we need to look beyond exceptions. What else can we do to try and balance these trade-offs a bit better? That's where we want to go. And you may have heard a lot of talk about ADT-based error handling. Seems to be the popular thing at the moment. If you haven't heard, well, I'm going to explain it now, so don't worry. So ADT stands for algebraic data types. Computer sciencey term. You don't really need to worry too much about what it means, other than that we've got product types and sum types, and it's sum types that we're interested in. So these are types that represent a choice of types. So optional is the simplest case, the choice of the value or no value. But then we've got variant, it's a choice of many values. And we're also going to look at this proposal for stood expected, which is a more sort of specialized variant. So probably best just to go straight to the examples. And for this case, I'm going to look at a really simple date class. So here's one you might write that does some validation in its constructor. It's more like a contract. It's not complete, by the way. It's not catching everything here. But if you call this with invalid data, it's going to, in a debug build, terminate at runtime. We may not want that. We may want to have that more sort of control flow based error handling. So let's have a look how we can do that by introducing a static make method. And that's going to return stood optional. That's where we're going to start. So as we said, stood optional represents either the value or no value at all. So first line, purely just doing that same validation again. If it fails that, it returns, we've got empty braces here, that just means an empty optional. Otherwise, it returns an optional containing the date. So we're using the brace initialization to cut a bit of the boilerplate out. If you don't know more about that, speak to Timo, he's the expert. So this is allowing us to use stood optional for error handling. Here's the usage code. So we'll try and make our date. Because optional overloads the Boolean operator, we can test it in an if. So if we have the value, we'll take the happy path, and then we can dereference the date like a pointer to get the value out. Otherwise, we call the error path. Just for sake of completeness, if you are doing this, you might also want to provide access to the unchecked version as well. And I like to spell it out so that it's really obvious in the code that this is the one that's going to terminate if it goes wrong. So that's just how I tend to do it. But let's have a look at the scores. So overhead's pretty good. I've given it 8s, maybe a 9 is justified. I think we're getting better at optimizing optionals now, but there's still some room for improvement. But it's up there. It's comparable to error codes on both the happy path and the error path. So more or less in the same camp as error codes here. But it's pretty safe as well. Even though we haven't used no discard here, because to get the value we wanted, we have to unwrap the optional, we still have to deal with that error case. So it's pretty safe to use. Not perfect, because you can actually dereference the optional without checking, but you sort of have to go a bit further to do that. But it is quite noisy. For the same reasons as before, it's all error, control flow error handling. It's all mixed up in if statements. We'll see more of that later, actually. No separation of paths, but very easy to reason about. I think this is even easier to reason about than the Boolean returns, because it's obvious that you're either getting the value or not, just from the signature. Again, it's like Booleans in that we only know that an error occurred, not what the error was. So that's one thing we're going to try and improve on. So the next sum type that we can use is stood variant. So like optional, this also came in C++ 17. By the way, if you're not on C++ 17, both of these types have been freely available in libraries like Boost for years. So if you're not familiar with them, do check them out. So variant allows you to specify a choice of multiple types. So here we can say either it returns a date or something else that gives us more information. We use a string here, but in practice you probably use some sort of custom error type, just to make it a bit simpler. So now we can be a bit more fine-grained about what errors we're returning. The usage code, so here we're calling, this is stud variant, boost variant's a bit different, but we're saying, does it hold this particular alternative date? And if it does, get the date out, otherwise get the string out. It's a bit verbose, I have to say, so that's going to be reflected in the scores. Again, overhead's about the same as optional. I'm putting the safety scores down a touch, just because it is quite hard to use to get this right. So I think it's a bit easier to misuse. And it's more noisy because it's so verbose. But we do get full marks for the message. We can output anything we want in that second type. So we're sort of getting there, but we've got trade-offs again. We can improve this a little bit. There's a form, get if, that will effectively convert it to an optional. So now we can treat it more like an optional, except in the error case, we can still get the string out. So that's an improvement. So yeah, I'll put the noise score up a bit there. We're getting somewhere, I think, but still too many trade-offs. So I mentioned one more sum type. We don't have it in C++ 17. This is proposed for C++ 20. So stood expected. Again, if you're using boost, boost outcome is similar to this. It's actually a bit different as well, but it's close enough. If you want to use that now without C++ 17, you can use boost optional. I'm going to talk about expected here. And this is very much like a variant with two types, but it's customized for error handling. So let's see how we use that. So in the signature, say it looks very much like variant. We've got date. String here could be any error type. But the usage code is now much simpler. Again, like optional, we can just test it with the conversion to bool. We can dereference the value to get that out. And in the case of the error, we just say .error to get that out. So much more closer to our intention, which is the whole point of it. So in terms of the scores, makes it safer to use, because now it's easier to see what the intention is. Has all the other benefits as well. Less noisy, but still somewhat noisy. And the other scores are about the same. But we're getting better. Feeling good about this direction, I think. But I talked a lot about composability, amongst other problems that we're still yet to solve. And I said that we don't really see it in these examples because they're only one level deep. It's when we want to compose things together that shows up. So I want to drill into that a little bit more. To do that, I'm going to introduce two functions that we want to compose together. So first one, toInt, it's just taking a string, converting it to an int. The second one, divide, we'll take an int and another integer to divide it by. So in both cases, I'm handling errors using stood expected here. So stood expected of int with string as the error type. Implementation is fairly straightforward. I won't dig into that too much. Let's have a look at how you would use this, though. So remember, this is stood expected, which is about the best we've seen in terms of expressive error handling so far. Just with two functions, the bits in yellow are the happy path, and everything else is boilerplate. And that really shows what the problem is. A lot of boilerplate. Now say, by inverting the flow, you can get a little bit of an improvement, but not much, and that's not always possible. So yeah, just following the logic here. It gets harder with every new thing that can fail. So there's got to be a better way than this. And there was a blog post by Simon Brand about a year or so ago now. Functional exceptionless error handling with optional and expected, which is a bit of a mouthful. But it's got the word functional in there. That's a key part. Because in functional languages, they've been dealing with this for years. They've got approaches for it. And as you might have guessed, it involves the word monads, which we won't dig into now. But this blog post does. Gives some good examples. And Simon proposes adding extra methods to optional and expected to be able to sequence these things together and doing the wrapping and unwrapping boilerplate stuff. It's got good examples of that. That was a blog post last year. Since then, in San Diego, in fact, originally in Rapperswil, he's proposed it for inclusion in C++ 20, which I think is going well. It's not been signed off just yet, but that's likely to be in C++ 20. So that'll be good. But in the meantime, we can actually do very similar with an external helper function that I called binderwave. And all the boilerplate at the top, it's not going to dig into it now, but it's just to allow us to use this in two ways. One is the case where you have something that returns something that's already a stood expected and just passes that on. And in the other case, a raw value, we want to wrap it in a stood expected. Usually you do this with two functions. I've just rolled it into one, and it's involved a bit of template boilerplate at the top. Don't worry too much about that. The important thing is the function itself takes a stood expected, it's all very generic, and a lambda. If the expected contains something, it forwards it onto the lambda, dereferencing it, and returns the result. As I say, depending on what that returns, it'll either wrap it in an expected or just pass it on. But if it returns an error, it's going to rewrap that error in another expected. The reason it does that is because they may be different types. So actually, the implementation is really simple. It's just an if statement and just adding that stood expected layer. But using this means that we push all of that boilerplate into a single helper function. So how does that make our example look? Well, it don't look something like this. And sure enough, all the if statements have gone, but we still have to walk through this. So now execution starts in the middle, the highlighted bit, calling toInt. That returns an expected that gets passed on to with, which will do our if, and then call our, if it contains a value, calls our next lambda, which will then forward on to divide. But notice this gets the dereferenced in, not the expected. So that composes nicely. And if that returns a value, that finally gets forwarded on to the last lambda to do something else with it. So we seem to have made some progress, but I think we've taken some steps back as well. This is slightly less code, but I think it's even harder to reason about because the logic's all inverted. So I'm not too happy about that. Let's have a quick look at the scores though. I think it's safer to use because the dereferencing is done for us. The boilerplate's been done for us. But I'd say it's actually more noisy, even if it's slightly less code. But we do have this nice separation of paths. Now the error handling is being handled for us by the helper code. Mostly, we just deal with wherever the error occurred, we deal with it in one place at the bottom. So we're starting to get somewhere, and I think it's easier to reason about as well once you get used to this style. And composability is great. That's exactly how this works through composability. So there's something here, but we're not quite there yet either. One of the reasons this looks so awkward is because C++ really sucks when it comes to functional composition. Functional languages do this much better. We can approximate it if we change the name of our function to an operator, and in particular a ternary, say an infix operator. So I'm going to use the pipe operator, which seems to be the common approach. But anything where the operator comes in between the arguments will do it. That's the only change I've made here. Now look at how this changes the usage code. Now, control flow starts at the top, called toInt. If that returns a value, that gets passed on to the next lambda on the next line. If that returns a value, it gets passed on to the next lambda on the next line. And as before, if we get a result, it pops out the bottom. So just by inverting that, it makes it look a lot nicer. We've still got a bit of boilerplate because of the lambda syntax. So I think we're in a much better situation than before. So again, the highlighted code is the happy path. The rest is boilerplate. We're definitely getting somewhere, I think. This is currently sort of the cutting edge of error handling in C++. Let's have a look at the scores. So again, that noise number has come up. It's still a bit noisy, as I said, but it's a lot better than before. Composability, actually it's the same, I think that's an error. But the numbers are getting there. Numbers are getting there. This is reassuring. But I mentioned functional programming languages earlier. So they deal with this stuff all the time. What we're actually doing here is we're treating expected as a monad. So we don't need to dig into exactly what that means today. You can always ask me later. But functional programming languages deal with monads all the time. They must have ways to make this even nicer. So let's go all the way to the top and see what Haskell does. So it's a page from the Haskell wiki, and it's got a note on do syntax. It says it's syntactic sugar for use with monadic expressions, for example, and it's got do. Now, set aside for a moment that do is a keyword in C++. This means something very different in Haskell. And within that block, you've got a sequence of imperative-looking statements separated by semicolons. Those semicolons are not like semicolons in C++. This is like the sequencing operator. What that will do is, as I said, it's shorthand for what's at the bottom. And if you imagine the greater than is like our pipe operator, and the greater than equals is like our other pipe operator, because I mixed the two together. What it's doing is it's converting that top thing into something very much like our previous example. So how would that look if we had a similar facility in C++? Well, let's just do a thought experiment, shall we? Here's our example again. Now, if we use something very much like Haskell do notation, we'll use do for now. We'll come back to the problem there. So now this looks much more like the type of code we want to write. Bear in mind, those semicolons, again, they're Haskell semicolons. But we need to pick this apart a bit. But let's start with the semicolons. You may have heard people talk about programmable semicolons in languages like Haskell. That's what this means. That's the thing that actually maps to the operator. That's where the magic happens. So let's just use another keyword for that instead. Why not try? Because that's expressing our error handling intention here. So if we say the try keyword is the thing that signals to the rewriting logic that we want to sequence this as a lambda, that's what that means. Now we've got our C++ semicolons back. Now I'm not too happy that there's a bit of the happy path still at the bottom, that final cout. Let's move that up into the do block as well. And at the same time, we'll add a function on the return type called catch that takes the lambda that will get called with the error value. So now we can handle it in a way that looks a bit more familiar if we're used to C++ exceptions. You can see how we're step by step mapping back to what we had before. Let's deal with the do keyword then. Since we've got a catch at the end, it makes sense to just call that try. Now obviously that's a contextual keyword because try already has a meaning in C++ in that position. We can only do this in a case where we know we're dealing with this type of syntax. We'll come back to that in just a moment. Don't worry just yet. In terms of the code you're calling, so we currently have this divide function, returns a stood expected. If we're getting the compiler to rewrite stuff for us, let's just have it do that if we put throws there. If we put throws on the end of a function, that means rewrite it to whatever our return type is, wrap it in a stood expected. Again, it's a mechanical transformation. Nothing else needs to go on here. And because now we've marked our function, throws, the compiler knows anything in that function, we can use this new style try. Remember I said contextual keyword? That means this new thing. That's the idea here. And instead of returning make unexpected, just do throw. Again, it's just going to translate it for us. And while we're at it, instead of having that function catch at the end, let's just make that a keyword as well. Just map back to the same thing. So hopefully you can see how we got to here from where we were with the monadic form of using stood expected. But it looks like exceptions. Doesn't have any of the problems of it. Let's have a look at how it scores. First of all, let's note, unlike exceptions, this is now fully marked propagation. We've got the throws keyword telling us that the function can throw. And we've even got that throw keyword before each expression that may throw at the bottom, so we can see any line that may actually emit an error. So that's an improvement on exceptions straight away. Look at the scores. Now we've got that magic error path figure. We're basically on par with error codes. In fact, it may even be possible to bump that up because the compiler knows about this. It can actually generate even more optimal code and make use of some known tricks to almost completely eliminate that overhead. It'll still be there, but it's mostly invisible. So optimistic, but I think that's achievable. Now look at what we got. It's almost 10s across the board, 10s and 9s across the board. And maybe you can quibble about the numbers, but this is where we want to be. I think we all agree. Almost no trade-offs. And this is not just a thought experiment. There's a real proposal behind this. It's got Herb Sutter's name on it. Same guy that wrote all those books on exceptions. It's called Zero Overhead Deterministic Exceptions, throwing values. Some of you may have already heard of this. If you haven't looked into this yet, I encourage you to do so, because I think it's going to change the whole world of C++, I think, but particularly areas like audio that are so low latency oriented. It's designed for this sort of community. So we really need your feedback on this to see whether it's going to bring more people into the fold of using a primary C++ blessed error handling strategy. So I'm running out of time, so I'm going to finish here and point out that there's loads of references to all of the proposals and lots of other things on my website, levelofIndirection.com/refs/cpp-optional.html. So you might want to take a photo of that, or you can come catch me on the booth and I'll give it to you. If you can't remember levelofIndirection.com, I've also got extra levelofIndirection.com that redirects there to make that a bit easier. But that's the end of the talk, so thank you. Good time for 1 or 2 questions?
We do have a few minutes for questions.
So that was great, thanks. So I suppose it's quite nice, it's great that you're using the monads to do the exceptions, but that's just one use case, right? A really nice example in Haskell is that they use it for transactional memory to compose transactions. But now you've added it now you're potentially adding it in a way that doesn't allow you to generalize. Obviously you could have a concept that's a monad, and then you could have an instance of it. Are they thinking about that? I mean, do notation. I mean, it's first class in Haskell as well, which is very powerful, and so sometimes it would be I think it'd be great to have that in C++, but it seems like you're not going to go that far this time.
So it's an excellent question, and can't give a full answer in the time I have available, but just to say that if you think of monads and monadic handling as a pattern, there's lots of different ways to apply that pattern, and there's lots of different proposals going through at the moment that deal with different approaches, coroutines as well. Big reason that coroutines is being held up is because people want to treat it very generically as a monadic approach, and that's a bit of a mismatch. There's also a very general monads proposal going in, and then there's a few other more specialized ones. I think this one deserves to be specialized simply because we can take full advantage of all the compiler optimizations that we need to make it solve all the problems that we've been having.
But the IO monad in Haskell, for example, is specialized. The IO monad in Haskell does have that exactly, and the exception monad in Haskell is specially treated in the compiler in the same way that you'd want to do it there, but it maps to the generic implementation, in terms of use case, if you see what I mean.
Yes, there are some nuances here which maybe we should talk afterwards, I think. But yeah, great question. Thank you. We've got time for any more?
Yeah, there's time for one more question. All right.
Okay.
Well, no more questions. Thank you, Phil.
Thank you.